Okay, here we go. Are we ready? Packets out, all that kind of good stuff. Now, at lunch, I got a little crazy and I emailed everybody that didn't have both of their lecture questions done. So if you got an email from me, it said or a message in Schoology, it told you what you had to do to make it up if you forgot one. So hopefully everybody got their lecture questions done. Let's talk about this quiz tomorrow. Not tomorrow. Today is not Thursday. Tomorrow is a lab. Okay, everybody in this room will do this lab tomorrow. Everybody not in this room will do the lab next Thursday. Okay, and we're going to try to get your hands on some endo, exothermic, all that kind of good stuff. The quiz on Friday is 9 questions and 30 points. Okay, 9 questions and 30 points. It is over Monday's lecture, which is all about temperature, heat, thermal energy, all that kind of good stuff. And then it's also over yesterday's lecture, which is endo, exothermic, entropy, and spontaneity. So we are going to practice all of that business. We're going to practice it all today. Okay. Those of you in here will take it in here on Friday. Those of you at home, you will take it between 7:30 and 1:30 on Friday. Okay. So what I need you to do is I need you to get out your packet. We're going to kind of work backwards in it for a second because there were some papers that we did not do. But before we get into that packet, one of the harder things, and there is a problem like this on the quiz, is knowing direction of energy transfer. So we're going to go back and you're going to do a little half-C sheet that was there that we didn't get to. We're going to make sure you can do that. And you're going to tell me direction of energy transfer. Now, let me give you an example. Okay. We know that everything in nature flows from an area of high thermal energy and temperature to an area of low. Everything goes from high to low. So here's a sample question I just thought of, kind of just to do a practice without taking your practice off the worksheet. It's starting to get, quote unquote, cold outside, correct? Mm-hmm. And because it's getting cold outside, you might want to wear a jacket. So this is you. You look awesome. Beautiful. It's a good look. Now, when you go outside, if it's cold outside, let's say, let's say it's particularly cold. Let's say it's 5 degrees Celsius. That's right around probably 40 degrees outside. That's pretty chilly, correct? When you go outside, are you hotter or colder than your outside surroundings? You're hotter, right? You're about 37 degrees Celsius. So you are high thermal energy, correct? And when you go outside in the winter, it is low thermal energy. So why do you feel cold when you go outside? Is cold applying onto yourself? What are you doing? You are perfect. You are losing thermal energy to the surroundings. Does that make sense? You're like, man. So next time you go outside, I don't want you to speak in a pro. You're like, man, it's cold outside. You'd be like, man, it's just lacking thermal energy out here. That's really what you should be saying, okay? You're going to be using it right now. So the question is, if I put a coat on myself, look at your nice puffy coat. It looks good. Yeah. If you put a coat on and a hat, on, is that doing anything to increase your body temperature? No. Is that doing anything to make the outside air not 5 degrees? No. What is it doing, that coat? It is, yeah. Perfect. The I word we're looking for is the fact that it is an insulator. So you are still losing energy. It's just happening slowly, a lot less, okay? Now, would you be like, guys, I have the best idea. I think we should start making coats out of copper. Yeah, you're going to be like, might be a little hard to move around, but that's okay because you're going to look slick. Would a copper coat help you stay warm at all? No, because it is a conductor, and therefore it will take your energy even faster. So the idea is you apply an insulator. That's why you have a blanket, all these fluffy insulation things. We use those, okay, to keep the heat transfer from our bodies out. Easy. So what you're going to do is if you go to your packet, wrong way, and started at the very beginning, packet. Take the first, I can't tell you how many times I lick my fingers with my mask on. Not the first page because that was the lab, the second page. I don't want you to do number 2. It's a waste of your time. But there are 2 of these heat scenarios I want you to talk about for me. The first one, when you wake up in the morning, okay, and you go into the bathroom and you step on the tile, what does it feel like? Feels cold. So what do? You jump onto the rug or the carpet, and that feels a little bit warmer, correct? What I want you to do is draw me a little energy diagram. So I know I clearly drew these so well. So just take, and this is 1 foot, and then this is tile. Take, this is another foot, and this is a rug. I want you to show me the direction of energy heat transfer, and I want you to write an answer to me, and I want you to tell me why the tile feels colder than the rug, which direction energy is going. Okay, and then how comes, and are these at different temperatures, your temperature, so you're going to give me that. You're also going to do number 3. How does styrofoam keep cold things cold? I understand how it keeps hot coffee hot, but how does it know to keep ice cream from melting? You're going to go ahead and you can talk to me about the difference between coffee in a styrofoam cup and ice cream in a styrofoam cup, and tell me the direction of energy transfer and how that all works. I'm going to give you 3 minutes for number 1 and number 3. If this was a test, if this was a quiz, how would you answer these? If these were tests or quizzes, talk to me. Are the rug and the tile moving? No, that's what I do. I would draw yourself a little, be like, draw a foot and draw a right tile. And draw a foot and draw a tile. And I want you to think about what your temperature is versus the floor. You write high where it's hotter and low where it's colder, and you always have to go from high to low. Okay, so give it a try. It's hard to like put together. Once I say it, you're like, oh, yeah. It was a little bit harder to put together. So give it a try. These are just practices. Like it. Give me a direction. High, low, where our energy is going. Who's high? Who's low? Which direction is energy going? Who's high? Who's low? Which direction is energy going? We're just in the packet real fast. We're actually moved back. We're on the 2nd page, so just jump on in here. We talked about the quiz. The quiz is 9 questions and 30 points. Yeah, fill in, drop down, drag stuff, you know. Nothing will be too crazy. All right. All right, so hopefully we're getting going on the first one here. We're just here on the first. So we're just doing these. We didn't get to these last at the beginning of the week, and there will be a scenario like this on the quiz. All right. All right, let's do this. So, and I do have popsicle sticks. I'm not going to do my popsicle sticks for this. I'll do my popsicle sticks for the harder stuff here. Boop, boop. So if anybody wants to answer, we can answer all of these together. When you walk into the room, okay, your feet are at about 37 degrees Celsius. You are pretty warm compared to the rest of the room. Are the tile and the rug at any different temperature from each other? They have been sitting there all night long, right? So they both, let's say it's a cooler day. Oh, I don't know. Maybe they're about 24 degrees Celsius. So if we're talking high and low, who is warmer, you or the ground? You. and the ground is a low, and the ground is a low. Now, everybody can usually go with me here and say the tile is what type of material? It is a conductor, so it quickly transfers energy away from your feet. You step on that, and it is taking energy just as fast as it can. You're like, woo! Okay, it's taking energy away from your feet and making you feel cold. Now, the misconception then is, well, if that feels cold and this feels warm, this carpet must be giving your feet some energy. But take a look. You are still hotter than the carpet. So which direction is energy going? From you into the carpet. But why doesn't it? Because it's perfect. I heard it. It's just going slower, less, okay, at any given time. It just can't do it as quickly. Okay, so it's not that we flipped directions. That's a very easy thing to think. Be like, well, that's warm, so it must be giving you energy. No. Okay, just be careful. Okay, perfect. All right, so I'll give you maybe another 30 seconds to clean up your styrofoam cup one. So if you want, just draw 2 cups really fast. If you have hot coffee, think about where is high, where is low, direction of energy transfer. If you have a cup of ice cream, think about what is high, what is low. Think about energy transfer. Good stuff. Let's take a look. Okay, if you want to fix up that question.
Is the second one the empty box?
Yeah, at the very bottom. Yeah, we're doing number 3. Yep. I skipped number 2. It's just like too simple. It's a waste of your time, to be honest. So just on to number 3. All right. 2 cups. One has hot coffee. One has ice cream. How can styrofoam know to keep them both the temperature that they need to be? Oh my goodness, styrofoam must be so smart. Perfect. Are we ready to get into it? I still see some people drawing. I don't want to cut anybody off. Here we go. All right, so the first thing, let's talk about the hot cup of coffee. You have a nearly boiling cup of coffee. Is the temperature higher inside or outside the cup? It's higher inside compared to your outside, which would be high to low. Stop with your face. You see nothing. Okay. I don't know why my smartboard likes to just, pop up on me like that. So which direction is energy transferring over time, making your coffee cool down? From in the cup, out. Okay. Everybody gets that. You see the steam coming off of it. You feel it warm when you're on, holding it. It's losing thermal energy to the outside. Would you want to put your coffee in like a metal cup? Number 1, it would burn you. And number 2, it would make it cool down very quickly. What's special about styrofoam? Styrofoam is an insulator, and it slows the direction of energy transfer. Now, what is wrong, but students will say, and it seems to make sense in your head, you're like, oh, okay, so styrofoam keeps things in, right? Yeah. So this ice cream must be really cold on the inside, and so the cold is trying to get out, and the styrofoam won't let the cold out. That's not exactly how it works, right? Because everything in nature goes from high to low. So what happens is your ice cream is a low temperature. I do agree with that compared to the high temperature on the outside. But the styrofoam isn't keeping cold in. It's doing what? Keeping hot out. Okay? So this heat is still trying to get in. It's still trying to melt your ice cream. It's just that styrofoam's like, yeah, no. Okay, slows it down. This is why when I watch TV, it pains me sometimes, like HGTV. They're like, oh my God, I'm going to insulate this house to keep the cold out. And I'm like, no, it's not keeping the cold out, keeping the heat in. Okay, so in society, we speak a little backwards sometimes. We should always speak in direction of the hot, okay, because there is no thing as cold. The reason why if you put your hand in some ice cream, it feels cold is because it's taking all your thermal energy as fast as it can, okay? Does that make sense? So just want to make sure that you know kind of how to do these things. You might see a good test question. I can think of one test question that I love on this stuff. So there will be a question on the quiz, and you can guarantee a question on the test over this type of stuff. Okay. Now, go ahead and turn the next page. That's our notes. And then wham! We didn't get to this yesterday. So this is going to be a recap. I'm going to pick out some popsicle sticks and bother people. Get ready at home. I'm going to bother you. Find your microphone thing. All right. In which direction, in or out, is energy going in an endothermic reaction? Endothermic. Anijah, T. Or I. Why do I have a T? I'm sorry. Endothermic. Energy goes in. Perfect. So this one, we can all do this together. Endothermic energy goes in. Exothermic energy goes out. So we're just refreshing. So if you weren't here yesterday, mentally or physically, or both, we're going to refresh. I'm going to do number 2 so that I can help you here. Number 2, I'm going to do together. I will not expect you to draw it on your quiz, but if you can draw it, then that means you can also pick out which one is correct on your practice worksheet in a second. Endothermic means I take energy in, correct? So if I'm looking at a graph and the energy is higher as you go up, that means at the end, my products, I want to be higher. And at the beginning, I need to be lower. And then the graph's kind of weird. You give it this like little hump and then you end out there. Okay. But the main thing I would use this to help yourself study is that it gains thermal energy. Okay, it's taking that energy in to create bonds, to create new molecules, to do things like that. So it's taking energy from its surroundings, and it's got more energy at the end. All right. Then if you wanted an exothermic, that means at the end we have less. At the beginning we have more. Remember, these are your products. These are your these are your reactants. These are your products. And you do a little bump, but then we end up coming down there. Again, I'm not going to ask you to draw it. If you could draw it, that means you know what you're looking for. All right, I'm going to bother somebody to tell me what entropy is. Who's going to tell me what entropy is? Ian M. At home, representing the at-home people. Ian, what is entropy?
Like how disordered the thing is.
You got it. Disorder. Thank you, Ian. It's the measure of disorder or the randomness. And the greater this disorder, the greater the entropy. So if you can think of entropy being the word disorder, then you are safe. Measure of the randomness, disorder, some people call it chaos, stuff like that. So it's what all is going on there. Okay. Then what we're going to do is we're going to fill in some boxes here. I'm going to have everybody give me 2. The lowest amount of entropy that we have, oh, everybody from home is just batting up here. Heather W. Heather, let's talk. The lowest entropy or the least disorder in your honors chem, it looks a little bit different. Do you know, Heather, the least disordered substance we have?
Crystals.
Crystals, and then come what?
And then solids.
You got it. Crystals and solids. They're very close in entropy. I'm probably not going to talk very much about crystals, but you're an honors chem, so you got to know about them. And then if we have a little more disorder, okay, they're shaken in place, those are solids. Who can I bother next for another one? Oh, not here. Ellie. Hey, Ellie. After a solid comes a liquid, and if I put stuff in that liquid, it's called a, you are with it. Okay. So again, liquids move around more chaotic. And then if you put something in your liquid, now you have a lot of stuff running around, kind of even more chaotic. The most chaotic thing, the most highest disorder we have, Savannah, tell me, what is the most disordered thing we have? That's a gas. Okay, so this is most. So some students, making sure that we know, if you move from left to right, you're getting more disordered. And if you go the other way, it's becoming less. Are you with me? Now, nature tends to favor one direction. Let's figure out which direction. Priscilla, how you doing today? Does nature want to make things more disordered or less disordered? Perfect. Nature always favors more entropy. Fires are going to burn, ice cubes are going to melt, things are going to get more chaotic. Okay. I've had about enough entropy in 2020. I don't know how much more I can handle, but here we are. Okay. It's just a high state of entropy. It's okay. Beautiful. Then we want to talk about a spontaneous reaction. Spontaneous reaction. Kayla, talk to me about a spontaneous reaction. I have this candle right here. Is anything helping this candle burn? It's just burning, and now it's getting wax everywhere because there's a hole in my thing. Oh, no. Okay. So spontaneous reaction means that it goes along without what? Perfect. It continues along by itself. Also, while I have you here, Kayla, there are two things that make something spontaneous. What two things make something spontaneous?
Exothermic and
You got it.
increase in entropy.
You got it. If you are one of those two things, you're going to happen by yourself. Okay? Feeling good? All right. So that was the recap of yesterday. What we're going to do now is the practice worksheet, and then I would like to light my desk on fire by the end of the period, and we are going to do practice of these things. We're going to do practice of these things in the lab tomorrow. Okay? Perfect. And there's also a bell work for those of you at home. So, next page in your packet. Look at us just like rolling through these papers now. I would like for you to do the front. I'm going to give you 5. I love talking, so I have a really hard time giving you time to just work by yourself because I never get to see anybody and I just love to talk. I'm going to ask that you identify if these are endo or exothermic. I want you to tell me, and I'll leave this up here so you can kind of see, or you probably have your notes on you. Is it becoming more disordered or less disordered? Going through, talking about each one, we can have a conversation about them. Then you're going to talk a little bit more about entropy. Remember, if you look at a chemical reaction, draw yourself a line right at the yield sign and you compare your reactants to your products. I have a liquid and a gas going to a gas and a gas. So overall, what's happening to the entropy from one side to the other? And if you can think in your head, all right, it's going from like here to here. That would be D. Is it going from here to here? So you're thinking about these boxes in your head. I'm going to give you 5 minutes for 1, 2, 3, and 4. Those of you at home, you're also doing this. I'm going to wander around. If you have any questions at home, I can answer them. Yeah. We're just going to do the front, and then we'll go over it. Oh, yeah, you're good. Thanks, son. You're okay. What's that? Right there. That's on 3, 4. Okay. 1, 2, 3, 4. I'm going to wander around. Put the jams on quietly. Usually people are like talking to each other, working on this, but you know. Oh, COVID. Let me check if any of my other people have come. Maybe you each want to try for me. Beautiful. And this might be didn't watch yesterday. This was brand new stuff. You wouldn't have ever learned that. Not something you have to break together. So the lecture is in Tuesday. Okay. Good stuff. You each want to try. Give it a try. Give it a try. These are practice. That's why we're doing them. We're practicing. 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 Hey, you just have to do the front. You can go into the back because we are going to do the 2 examples on the back, but those are a little bit harder. So we will do what we can do. Perfect. I gave everybody a try here. Bottom here, you can do this too. We're going to go gas, gas, liquid. Is that increasing or decreasing its entropy? Any questions I can answer? Possible. So you have like a sugary solution stuff. You put it in the freezer. Okay, so it's an aqueous solution. I'm going to put it in the freezer. What's it going to turn into in the freezer? Molten iron. Molten is like liquid iron. So if I got iron so hot it was liquid, then it turns into a hard nail. It's the almost the exact same thing. Liquid. Yes, yep. And then a can of Coke, like here. It's in there. There's a whole bunch of stuff in it, right? When you open it, it goes, what is that? Is it a solid coming out in here? It's gas, right? So it goes from aqueous solution to a gas. Question. Yes, fluid, solid, absolutely. Very good. We are going to, but if you want to wait, we'll go over it right now. Let's do it. Let's do it. We're ready. We're going to do it. Picking out some popsicle sticks, bothering some people. Woo! Should be good. All right, the first graph. Tell me, is it endo or exothermic? Mr. Harris. We just spoke, but do you have a guess, a stab at it for me? You're actually going to take in more energy. You have more energy at the end. Does endo or exo sound like it takes in energy? Endothermic. If it asks you why, you would say it takes in heat energy, more energy at the end, whatever. Very nice. Okay. Making that easy for the second one, if we have, so I'm a little reactants products. If you start with more energy and you have less at the end, that means that it is exothermic. Did you get those right? Boom, you're going to get that right on Friday then. Easy peasy. All right, let me bother somebody making Kool-Aid. Who's going to make some Kool-Aid for me? Aiden. More. Okay, and if you ask for a little support, okay, you would say it goes from a solid to an aqueous, and therefore it's going to get from this area to this area. Remember, this is more and this is less. Okay, perfect. Freezing a popsicle. I'm going to take a solid. I'm going to take an aqueous solution, turn it into a solid. Very good. That makes it less disordered. I'm going to cool an iron nail. Ian. Which one? I can't read if it's a P or a D. E and D. What do you think? When you have molten iron, Ian, and it is a liquid, and you cool it into a nail, it's going to turn it into a solid. That is doing what with its disorder? You got it. Okay. Opening a can of pop. This one's actually quite challenging. I think it's a good one. That would be a great V. Hey, V. Are you there?
Yes, I'm here.
Thank you. All right. You have a can of pop, and it has a bunch of stuff in it. It has sugar and food coloring and water and all this other kind of stabilizers and stuff. So it's an aqueous solution. Can we agree with that?
Yes.
Perfect. When you open it up, it goes, right? You hear this like opening sound. What do you think that is coming out? Liquid, solids, crystals, or do you think that's a gas coming out?
It's a gas.
It is a gas. So what is happening to my entropy when I open that can of pop? I'm sorry, what's happening to the disorder?
More disorder.
Perfect. Has everybody seen an Alka-Seltzer tablet? You chuck it into some water. Who's going to tell me what happens with it? Amani? Talk to me. It's a solid, right? You put it into water. Two things happen. It dissolves. And do you see bubbles? Have you ever seen an Alka-Seltzer tablet? You see some bubbles. Which of this would bubbles be? Perfect. So we're going from a solid to aqueous, solid to gas. That means it's going to, you got it. Perfect. Very good. Does anybody have any questions on those? I'm going to do the next ones because they're like exactly the same and it's just silly that we even did that. But if you have a liquid vaporizing, you're going to be more, increase, I guess it says increase or decrease the entropy. A gas liquefies, decreases. A solid melts, is going to increase. And then a solid dissolving in water is also going to increase. Perfect. All right, I'm going to bother somebody to do all 4 of these with me. Ooh, well, maybe I won't because we need more popsicle sticks. Wyatt P., are you here, Wyatt?
Hello.
Perfect. I have a gas and a gas are going to come together and make a liquid. What's going to happen to my entropy?
Decrease.
It is going to decrease. Who else can I bother? Preston. We got a solid and an aqueous solution going to an aqueous solution and a gas. And you're like, well, wait a second. This didn't really change much. Okay, so cancel those out. If I have a solid go to a gas, what's happening to my entropy? That's right, it is. Next one. I can bother you. Read. Tell me. In this reaction, is the entropy going to increase or decrease? What? You're with me. I didn't give you any help like I've been giving everybody else that. I have a gas and a solid. My solid stays a solid, but my gas comes to a solid, so that's going to decrease. You got me. And then last but not least, my last one here, Khalees. How are we doing, Khalees? Okay. We have a liquid and a gas going to a gas and a gas. So again, this gas doesn't really look like it's changing, but my liquid goes to a gas, so the entropy is, you got me. Okay, any questions on those? You'll be ready for the quiz on Friday. Let's do one more thing. These are where it gets hard because this is where you got to put it all together. Imagine you're sitting next to a fire on a cold winter night. Ooh, fire. Is the fire, you can just write this down, we'll go over it. Is the fire endo or exothermic? And explain. Is it increasing or decreasing entropy? So again, you're sitting here. I just love drawing things because I feel like you kind of feel better. My log. Think about when you have a log and you burn it. Okay. The fire is roaring. It's going. Okay. So how does it feel? That will tell you if it's endo or exothermic. What's happening to my log? Once it's going, is it spontaneous? Yes or no? And if it is spontaneous, tell me if both the factors are making it spontaneous or just one is or just the other is. So this is like, you'll see 2 of these problems on the quiz on Friday. So I'm going to put the music on, wander around. Anybody at home have any questions? No. All right, see if you can't answer these. They get a little challenging. Oh my God, I only have 5 minutes. What have I done? Can you answer this? If you want to do the wax one, you can too. I was going to demo it, but... This is exactly what it will look like on your quiz. You will have questions like this, 2 of them. You'll have to be able to explain the spontaneity to me. Oh. Good. Give it a try. Perfect. And if you're chilling there, if you have your laptops open, you do need to do your lecture questions, but that's at the bottom of the list for me right now. I'm sorry, participation points. All right, so let's talk. Who am I going to bother first? Elizabeth V, are you here? Fire. No. She says no. All right, we don't have time for this. All right, so we'll just talk it all together here. Are you ready? We have fire. When you sit next to fire, what does it feel like? Warm. It feels like fire. So energy is going from the fire to you. So is this endo or exothermic? That's exothermic. Releases heat energy. My log here goes from a solid to what when you burn it? It goes to a gas, it turns to ash, but basically what's happening to the entropy? It is increasing. Okay. So once you get your fire started, does it go by itself?
Yes.
Perfect. So it is spontaneous. Talk to me about the spontaneity. What is driving it? Talk to me. One or both. Which one's making it spontaneous? Okay, the entropy and the fact that it is exothermic. Okay, so both of those. Let's do one more because this is the harder one. Oh, goodness, stay with me. I still have 3 minutes. Don't pack up. I have a candle. Okay, I want you to think about the temperature of this wax right now. You ready? I'm going to take that candle wax and I'm going to pour it out. The candle doesn't fall and I hurt myself. Okay, and I'm going to pour it out onto the countertop kind of here. Now, I have a blob of wax here. Is it going to cool and harden all by itself? Do I have to do anything to it? I want you to do the exact same thing. And the hardest part, I put it into two. As the wax hardens, is it gaining or losing energy? So is it endo or exothermic? And what's happening to the entropy? Okay, it is tough stuff. This one is tough. Let's see if we can do it. Everybody likes to get the second one wrong. All right, you have liquid wax sitting on my countertop. Is the liquid wax going to gain energy or lose energy to cool and harden? It's going to lose energy. So if it loses energy, is it endo or exothermic? Exothermic, which we like. That's like, yeah, hey, we're doing the right way. But my wax is going from a liquid to a solid. So my entropy is doing what? Decreasing. So is it spontaneous? Yes. But why is it spontaneous? Because it's exothermic and nothing else. Okay? The entropy is not helping anybody. What is helping is the fact that it's exothermic. Okay? And I didn't get to light my desk on fire, but I'll do it tomorrow at the end of the lab. We'll do it. We'll get it going.